Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed the divergence of electric field and we have come across a new concept, that is Dirac delta function. Right? Now today I will discuss the curl of electric field and later on you will understand the concept of electric potential from curl of electric field. Now in vector calculus, the curl is a vector operator that describes the infinitesimal rotation of a vector field in three-dimensional space. At every point in this field, the curl of that vector field is represented by another vector which is perpendicular to the plane of the vector field which is rotating. So we will get another vector which is perpendicular to the plane of the vector field which is rotating. Okay. Now the direction of the curl is actually the axis of the rotation, which is actually determined by this right hand rule. Here the direction of the thumb is indicating the direction of the curl and the direction of the tip of other fingers is showing the direction of rotation. Okay. Now the magnitude of the curl is actually the magnitude of the rotation and it is measured by the length of the vector along the axis, which is along the direction of the thumb. Now if a vector field represents the flow velocity of a moving fluid, then curl is the circulation density of the fluid. Now to quantify the curl of any vector field which is rotational in character, let's consider a small closed loop. Here the arrows are indicating the direction of the vector field and this closed loop forms a small open surface area, that is ds, and n cap is the normal direction of this surface. Now the curl of the vector field is defined like this, which is limit ds tends to 0 closed line integral v dot dl divided by the surface area ds. Now this ds is elemental surface area and here this is very small, that's why we are taking this limit. Okay, so this is actually one form of Stokes theorem. This is one form of Stokes theorem. Okay, now we have to remember this form of Stokes theorem because we will apply this later on. Then if we do the detailed calculation, we can write this form of curl of vector field. This is similar to A cross B, which you have studied in your 11th class, right? Now here instead of A vector, we have del operator. What is del operator? Del operator is a vector operator, that is I del del x plus j del del y plus k del del z. And we have to do these partial derivatives on different components of the vector field. Here this Vx is the x component of the vector field V. Here this is y component of the vector field and this is z component of the vector field. Now here one thing you should remember, that this x component of vector field can be combination of x, y and z. In many cases it is combination of y and z only. It is not dependent on x. It may happen. Similarly, it can happen for other components also. Okay, so this it doesn't mean it is x component, so it doesn't mean that there will be only x variable. So there may not be any x variable, only y and z variable. Okay, so that you have to remember. Now let's find the curl of electric field where the electric field is of Coulomb type, and that is the electric field due to point charge, and that is this q by 4 pi epsilon naught r square, right? And this r cap direction is along the radial direction. Okay, so here this r is a one particular point where we want to find out the electric field. Okay, now this r cap is actually the unit vector along this radial direction, right? So this r cap can be written like r vector by r. So already there was r square, so it becomes r cap by r cube, and this is the constant which comes out from this operator. So that means we have to operate this curl on r cap r vector by r cube, and r vector in spherical coordinate, you know that this is I cap x plus j cap y plus k cap z, and r means root over x square plus y square plus z square, right? So let's do this operation. Now if we do this, then the I component will be like this. How it is coming? So let's do that. I component. So in I component you have to operate this del y on this z by x square plus y square plus z square to the power 3 by 2, right? Then minus of del z y by x square plus y square plus z square to the power 3 by 2. So when you operate del y on this, there will be minus 3 by 2, then 2y, right? So that's why it is 2yz minus 3 by 2. Similarly here also, and if we do the for other components, we will get these two terms. Now you can see here this term and this term will cancel, here also this term and this term will cancel, and here this term and this term will cancel, and we will get this curl of r cap by r square will be like this, right? So that's why we are having curl of electric field is 0, right? So it tells us that the electric field is irrotational field. It is not a rotating field, right? Now this is very clear from this picture. Here you can see the field lines are coming out. That means it is diverging in nature. So not rotational in character, right? So now if we apply the Stokes theorem, which we have seen here. So if we apply the Stokes theorem, then this will be the line integral, closed line integral E dot dl will be 0, right? So today I am ending here. In the next class we will discuss this equation in more details, and from there the conservative property of electric field will be discussed. Okay, thank you.